Hello, everyone. Welcome back. Today, I want to talk about three probability rules which are covered in elementary probability and statistics class. Before I give you an example, I'm going to just review these three rules. Forget about the base rule for the moment. I'm talking about three basic rules that we cover. So the first rule is the union rule, or sometimes we would call it addition rule. And it's to calculate the probability of the union. So we have the summation of the probabilities, but be very careful with the double counts. So you have to subtract the probability of intersection if it's not zero. If they are mutually exclusive, then you simply add. You don't need to subtract because the probability of the intersection will be zero. So if A and B are mutually exclusive, then you only need to add. Then probability of A union with B equals the sum of the probabilities. That is actually one of the three axioms of the concept of probability, but this rule is more general. The second rule is the complement rule. It says that the probability of a complement equals 1 minus the probability of A. Sometimes it's difficult to find the probability of a complement. Well, maybe I should use the other way around, because sometimes you want to calculate the probability of something, but that something is kind of hard to find. The probability of that something is kind of hard to find. So you consider it's a complement. So maybe that would be a better version in terms of practice. But essentially they're the same. Okay. So when you look at the problem which says some at least, at most, so at least is something like greater than equal to. So at most, less than equal to. You should think about this rule. It's not guaranteed that you're going to always use that, but it's better to think about the rule whenever you see at least, at most. Then you decide whether you want to use it. And the third rule is the product rule of probability, which is to calculate the probability of intersection if the conditional probability is known. Okay. So these are the basic rules that we cover in elementary probability and statistics class, while base rule is another topic we're not going to cover today. So I'm going to use one example to show you. The example is really some kind of artificial, not really a word problem with some particular practical meaning, but it's kind of illustrative, so I think it would be nice. Okay, so we have this problem. We know the probability of A equals 0.6, the probability of B equals 0.7. There will be different additional condition. So I wanted to emphasize that if you know the probability of A, probability of B, then you basically don't know anything else. You need to know something which tells us the relationship between A and B. Then everything else will be known. Okay, so you know the probability of A, probability of B, and then you know something else about their relation, then everything else will be known. Okay, so remember that. We're going to use a bunch of things, three rules, Venn diagram, okay, to solve these problems. But again, the purpose is to illustrate these rules, not applying them in real world situations. Okay, so let's look at A. The probability of A union with B equals 0.8. And we're looking for the probability of A given B. Now, one common mistake is that people just assume independence, right? So they're we're gonna use the union rule. So we have the probability the sum of the probabilities, and then you subtract the probability of intersection, and then they plug in numbers. Actually, I have seen a lot. 0.6 times 0.8, so 0.7. This is quite wrong because in general, you're not able to assume independence, especially some other information is given. Now, sometimes we do assume independence. For example, you toss a coin, you select a random sample, you roll die many, many times, and we do assume independence. But many other times, when you have, especially when you have some information which tells us the relation between these two events or these two sets, then you cannot assume that they're independent. Maybe you're conflicting with each other. Okay, so instead of doing that, you need to use this information and get everything else. Okay, I mean, you do know that, then you know something else which tells us the relation. Okay, so how should we do that? We're looking for the probability of A given B. So using the definition, that is the probability of A intersect with B divided by the probability of B. Now we know the probability of B, so we only need to know the probability of A intersect with B, but do not assume they're independent. Okay, if you are assuming independent, then obviously the probability of A given B would be just the probability of A. All right, then there will be no meaning to, not particular reason to ask that question, because you're assuming they're independent, then you say they're independent. So that's really not the point. Okay, so how to find the probability of intersection? So sometimes you use the product rule, right? But the product rule, you need a conditional probability, which you don't have. So you think about a rule that connects the probability of the union and the probability of intersection, which is actually a probability of union rule. So we're using the probability of union, we're using the union rule backwards. That's what we're gonna do. So probability of union equals the probability of A plus the probability of B minus the probability of A intersect with B. And we know the union, the probability of the union is 0.8, 0.6, 0.7, and we know the probability of intersection. All right, that is 0.5, right? 1.3 minus 0.8, that's 0.5. And then we get the probability of A given B, so we can go back to the equation upstairs. All right, so this would be equal to 0.5 over 0.7, so just make it 5/7. You can write it as decimal, but 5/7 should be okay. All right, so this is about the union rule, using it backwards. All right, move on to the next one. Oh, by the way, they're not independent, because you can argue that the probability of the intersection, which we calculate is 0.5, which is not equal to the probability of A given B, probability of A times probability of B, okay, which is actually 0.42. Or you can argue probability of A given B is not equal to the probability of A, because we calculate both. That's fine. Either way is okay, they're equivalent, assuming the no probability is 0. All right, let's move on to the next small question, sub-question. The setting of this type of problems is that these things will be used throughout the sub-problems, but each sub-problem has some different conditions. Okay, this is the common setting. So we still have the probability of A 0.6, probability of B 0.7. All right, so let's move on to B. We know the probability of A given B is 0.4. Okay, so that tells us some information about the relation. Okay. And let's copy these two numbers. Okay. Make sure they're the same. Yeah. Now we're looking for, we know the probability of A given B, and then we are looking for the probability of B given A. We can use so-called Bayes rule, but really we don't need for this problem. We simply use some definition of the conditional probability and product rule of probability. So let's start with the definition of a conditional probability. That is the probability of B intersect with A over the probability of A. We don't know the probability of the intersection, but we can use the product rule of probability, but conditioning on B. So in essence, it's kind of a Bayes type of problem, but we don't need to emphasize that for the moment. Okay. So we know the probability of A given B, which is 0.4, and then probably B 0.7, and then 0.6. All right. So you have a 0.28 divided by 0.6. I think you can get rid of or multiply by 100 and get rid of not 12, 4, 7 out of 15. Okay, so that's define the conditional probability knowing the other conditional probability. Okay, so let's move on to the next one. Oh, there's another thing. Determine if A and B are disjoint. They're not disjoint because the probability of the intersection is not 0. 0.28. All right, it's not 0. Disjoint means the two events are disjoint. That means they don't have intersection. The probability of the intersection is 0. All right, so the next one is we're looking for the probability of A union with B, given that they are independent. All right, so that's very natural. Most of people would get it right. You have the probability of the sum of the probabilities and minus the probability of the intersection. And then using the independence, that is simply the product of the probabilities. Right, it's 1.3 minus 0.42. That is 0.88. All right. All right, so next one, it's better to use Venn diagram, but if you don't want to, that's fine. If you have a very clear mind about the type of complement rule, okay? So for example, I saw people do that. That's totally fine. Minus the probability of A. Oh, actually, that is kind of okay to use that. So probability of A is 0.6, probability of B prime, use the complement rule. That's 1 minus 0.7, so you have 0.3. And then we are given the 0.2 here. That's 0.7. But like I said, if I tell you probability of A and probability of B and something else, you should know everything else. Okay, something else about the relation, then everything else is known. So I can give you other random things, like probability of A prime, for example, you intersect with B equals 0 point something, all right? Then you are not able to use this addition rule directly. You need to do something else. So that's why sometimes for this type of problem, you cannot use directly those rules sometimes, because this one actually you're okay. It's better to draw a Venn diagram. To draw a Venn diagram, a key is to find sort of the middle part, which is the intersection, okay? Let's draw a Venn diagram. So you have A here, you have a B here. And we have the universal set or the sample space. It doesn't really matter what you call. So how can we figure out the Venn diagram? We need to put numbers there, right? Number on each piece. And sort of the key is to find the number of this piece, which is the probability of the intersection. All right, so we know the probability of A intersect with the probability of B complement. So you try to understand what that means in Venn diagram. So you have a probability of A, but intersect with B complement. So this part should be gone. So what it really means is this piece, okay? Probability of A intersect with B complement. That's what this piece is about. So we know this piece is 0.2. So let's put 0.2 here. And we know probability of A is 0.6. So I know this is 0.4. And I know the probability of B is 0.7. So I know this is 0.3. By the way, we never put 0.7 for this piece. Okay, it's just very awkward and harder to deal with. So then we have a 6.1 here. Okay. So you see everything else is known. All the probability of the intersection, the probability of the union, the probability of the union complement, all these things will be known. Okay, so what is the probability of A union with B complement? So try to figure out that region, okay? First of all, it's a union, so everything in A should be in B. Everything in A should be in A union with B complement. So this should be included. And everything in B complement should be there. So everything in B complement should be there. Well, this piece is kind of a double counted, but I don't really care. So the only thing left over is 0.3. So it's just 1 minus 0.3. It's 0.7. Or, of course, you can add 0.2 plus 0.4 and 0.1. You still get 0.7. Okay? So I'm just using this simple artificial example to illustrate 3 basic rules. We don't have a lot of words. It's not a practical problem, but I hope that you understand these 3 rules better now. Thank you for watching, and I'll see you the next time.